Welcome, my name is Lucas Escabora from the University of São Paulo, and I will present my work entitled Enhancing Recursive Graph Querying on RDBMS with Data Clustering Approaches. The relational model provides fast and secure data representation, storage, management, and retrieval. Nowadays, several applications employ the relational model by using Relational Database Management Systems, or RDBMS. Here we exemplify three of these applications. The first one is the support of decision-making tasks based on data analysis and mining. The second one refers to manipulating complex data, such as images and videos. And the third one consists of supporting the execution of topology-aware queries. Topology-aware queries are similar to graph querying tasks, focused on the interconnection among the elements stored in the RDBMS. Processing day enables some interesting analysis, as exemplified in this slide with the following queries. The first one: find me the closest point of interest, for example, hospital, supermarket, shopping mall, given my current location. The second one: suggest me the best flight route from my home to my chosen destination. And the third one: search for unhealthy citizens within 5 blocks from a chosen hospital. Based on this analysis, our interest is in performing topology-aware queries within an RDBMS, not just executing such queries, but having high performance in its execution. Up to our acknowledgement, in the literature, many approaches deal with these queries by materializing paths using recursive queries, which results in executing several join operations through relationships of cardinality many-to-many. However, this approach does not consider the physical data organization. They often present the disk locality problem, or require external graph materialization, or employ specialized structures that also require customized management. Hence, our proposal focuses on improving recursive query performance by using clustered physical designs and without requiring extra processing, neither SQL language modifications. In other words, we propose a clustered physical design based on clustered tables approaches to improve the performance of topology-aware queries. As I said, our goal is to improve the performance without any specialized structure or SQL adaptations. The clustered tables approach has the task of assigning the data of each cluster to a location on the disk. In other words, when two or more data belong to the same cluster, they will be more likely stored close to each other inside the storage unit, such as in the same disk pages considering a hard disk. As shown in the image, such an organization enables us to gather the neighborhood of each vertex of the graph in the same disk pages when storing them in a RDBMS. Now, for this presentation outline, we already covered the introduction with motivation, topology-aware query examples, and our objective in this work. The following sections are divided into 2. Background, 3. Proposal, 4. Experimental evaluation, and 5. Conclusion. For the background, we cover the graph definition and storage, some specialized storages, and the execution of recursive query within RDBMS. When managing a graph in an RDBMS, the most common approach is to represent them as relations or tables. The vertices are the entities, and the relationships or edges are stored using an edge list representation. Other specialized storage includes variations of adjacency list representations. For instance, DB2RDF aggregates different properties from vertices and edges into the same column, SQL graph is an extension of DB2RDF for NoSQL databases, using JSON to represent the data. And finally, EdgeK aggregates multiple edges by their source vertex, which allows storing multiple edge destinations in distinct columns. For the recursive queries in RDBMS, its general definition consists of repetitive join operations of the edge table. In this case, the examples include the frameworks FEM and Grail. One way to represent such recursive queries is by using common table expressions to materialize paths and enable transversal queries. Such queries are declared using the with recursive statement and uses the symbol TI to denote each recursive step. An example of common table expression in RDBMS is the with plus proposal that includes relational operators to assist these recursive queries. Finally, other approaches based on external graph materialization includes GSparkL, Ringo, Graphite, Empty-Headed, and GR-Fusion. Next, we cover the proposal with the clustered tables methods, the cluster size estimation, and the graph query definition employed. First, we have the conventional approach for storing graph within an RDBMS with no physical optimization. Second, we propose the edge clustered tables approach, a physical organization that only employs the physical design of clustered tables over the edge table. And third, we also proposed the combined tables approach, which combines both vertex and edge tables into the same clusters. For the cluster size estimation, in the combined tables approach, we employed a cluster size large enough to store each vertex and all its adjacency list into a single cluster. In each cluster, we use it as the cluster key, the source vertex ID, and the objective of this approach is mainly to optimize the first join operation. In the edge cluster table approach, we used two cluster sizes following the Pareto principle or the 80-20 rule. In other words, we had chosen cluster sizes corresponding to 20% and 80% of the adjacency list size present in the graph. In practice, the values were chosen based on the quartiles 20 and 80 of the distribution degree sizes, and for the sizes of the clusters, we multiplied these values to the edge tuple size, which are in bytes, as you can see in the slide. For the graph query definition, we expressed the graph navigation using common table expressions by defining two queries, the starting point query and the recursive analysis query. The starting point query consists of a query that filters a subset of vertices to start the recursion. The recursive analysis query consists of each step of the recursion, which is composed of another join operation with the edge table. By combining both starting point and recursive analysis queries, we have the definition of the graph query used in this work, which materializes the paths by performing the union operation over every recursive step. If no max recursion depth is provided, it stops when the new recursive step is equal to the previous one. Hence, our objective in this work is to improve recursive or graph navigation query performance by using clustered physical designs and without requiring additional processing, neither changing the SQL language. For such goal, we employ the clustered table approaches. Next, we cover the experimental evaluation, describing the application scenario and three analyses of recursive queries performed over it. The application scenario comprehends a georeferenced complex network, where the vertices contain the coordinates in latitude and longitude, and edges have the distances in meters between each vertex. For the starting point, we simulated public facilities such as hospitals. We used the DIMAX dataset, which has around 24 million vertices and 58 million edges. Our experiments were carried out in Oracle 90C with Docker 90. For the cluster sizes, we used as the parameters the max degree of the graph, which is 9, and the 20% and 80% of their adjacency list sizes, which corresponds to degrees 2 and 3 respectively. And for the edge size, we used 25 bytes, which corresponds to its maximum size in the edge table. Given these parameters, the cluster sizes used in this work were 256 bytes for the combined tables approach, 50 bytes for the edge cluster table using 20%, and 75 bytes for the edge cluster table using 80%. These parameters resulted in different structure sizes when storing the cluster tables in the RDBMS. For example, both edge cluster table approaches are similar. They are around 20% larger than the conventional approach, and the combined tables approach is almost 3 times larger than every other evaluated approach, as you can see in this graphic. We divided our analysis into 3 experiments. The first one considers executing a recursive query for a single starting point. In this case, we evaluated not only the average query time, but also the number of buffer gets performed. The second one is focused on a selectivity analysis of the starting point query and its impact over the first recursive step. And the third one consists of evaluating the recursive query performance when starting from multiple points. For the first evaluation, we varied the maximum distance of the recursive paths up to 40 kilometers. In this scenario, the edge cluster table approach with 20% reduced the query time when compared to every other approach, as you can see in the green curve of the graph shown. To summarize these reductions, the edge cluster table approach, using 20%, reduced the graph navigation processing time of up to around 23% when compared to the conventional approach, around 24% when compared to the edge cluster table with 80%, and around 21% when compared with the combined tables approach. Still considering the recursive query starting from a single point, now considering the buffer gets, which corresponds to the accessed disk blocks, every clustered approach proposed in this work reduced up to 61% the number of accessed disk blocks. However, as you can see in this graphic, for paths greater than 20 kilometers, or in other words, 24 join operations, the number of accessed disk block is similar in every evaluated approach. For the selectivity analysis, we variated the starting point size through 9 values of selectivity. For each selectivity, we focus on maintaining the proportion of the graph distribution degree, as shown in the graphic. In the experiment, our focus were in evaluating the performance of the first join operation. The combined tables approach reduced up to 50% the query time when compared with the conventional approach, while edge cluster table with 20% reduced 37%, and the edge cluster table with 8% reduced around 36%. Considering only the clustered approaches, the combined tables reduced around 46% the query processing time when compared with edge cluster table 20%, the second best approach here. The second experiment shows that, despite the structure size of the combined tables approach be 3 times larger than the other approaches, It presented the best results for the first recursive step, which corresponds to returning the direct neighborhood of a vertex. Finally, we evaluated the time reductions when executing a recursive query starting from multiple points. We started a graph navigation query from a starting point query with the number of vertices of 5,000, 10,000, 20,000, 50,000, and 100,000. In each query, we evaluated paths up to 5 kilometers. In every query of this third experiment, the edge cluster table approach with 20% showed the best results, and here we summarize the reductions of it when compared with the conventional approach. When starting from 5,000 vertices, the reduction was of around 9%. When starting from 10,000 vertices, the reduction was of 10%. When starting from 20,000 vertices, the reduction was of around 15%. When starting from 50,000 vertices, the reduction was around 20%, and when starting from 100,000 vertices, the reduction was of around 11%. This last experiment shows that, in the overall, the best approach for graph navigation queries is the edge cluster table with 20%, because it presented the best curves when starting from a single and multiple starting points. Finally, we covered the results of this work, which includes the contributions and future works. To summarize, we proposed a physical design to optimize recursive queries in RDBMS without requiring SQL language modifications. By using cluster tables, we reduced disk I/O operations and the query processing time. Based on the cluster tables, we proposed two variations: the combined table, which combines both vertex and edge tables into the same clusters, and the edge cluster table approach, which only clusters the edge table. Our contributions were: when starting a recursive query from a single start point, we reduced the query processing time by up to 22.5%, and the number of pages accessed by up to 61%. For the first join operation, we achieved a reduction of up to 50%, and when starting from multiple starting points, we had an overall elapsed time reduction of up to 20%. For future works, we seek to: first, analyzing other parameters for the cluster table approach. Considering the cluster sizes, we can evaluate the Pareto principle rule in the combined tables approach, aiming at reducing the structure size, which was around 3 times larger than the others. We intend to see if the reduction of 50% of the first join operation is maintained. For the edge cluster table approaches, we used only 2 parameters for the cluster sizes. Hence, we intend to evaluate more parameters, such as other quartiles over the distribution degree sizes, or estimating the parameters based on some graph metric, for example, its diameter, or a parameter based on the RDBMS internal configuration, such as the disk page sizes. Moreover, we also intend to evaluate our physical designs proposed in this work over other categories of complex networks, such as social networks. And second, we also seek to combine the physical design optimizations proposed here with query optimizations, such as the with plus method, with therefore new relational operations to optimize the query execution, query rewriting techniques, a user optimization technique in RDBMS, and employing parallel approaches when executing the graph navigation queries. Thanks for your attention. For more details, please see the manuscript. I would like to explicitly thank the Brazilian funding agencies that provide financial resources to make this research work possible: FAPESP, CAPES, and CNPq. If you have any questions, please send me an email.